Okay, so let's start. Any questions from the previous class? No questions? Okay, so in the last class, we were essentially trying to look at bounds on the probability that an arbitrary function of n random variables deviates from its mean. For most of the course, we've seen bounds on quantities of this form, that is a probability that some linear combination deviates from its mean by some particular delta. And we saw that if these xi's are either sub-Gaussian or sub-exponential, then we can in fact derive exponential tail bounds on this particular probability. But really, what can we say about more general functions, which is really what we want in many applications, right? So the first step essentially in this approach is using the Efronstein inequality, which doesn't really give us exponential tail bounds. All it tells us is that the variance of any function of n random variables is upper bounded by this. This can be upper bounded in a number of equivalent forms, right? So in itself, the Efronstein inequality is not particularly helpful. It's sort of like what we had with Markov's inequality. But in many cases, if we impose additional constraints on the function, if we assume that the function has some more structure, then it turns out that we can in fact prove exponential tail bounds for functions as well. So the first class of functions that I introduced in the last class was these functions with bounded differences. So what are these? These are basically functions for which the function value can be arbitrary. It can be as big and small as you want. But then if you allow variation in only one of the variables, then it doesn't deviate too much. So changing the value of one variable doesn't deviate the value of the function by too much, right? And by using the Efronstein inequality, we can prove that if a function has the bounded differences property, then we have this upper bound on the variance. But in fact, we can prove something even stronger. As it turns out, if a function has the bounded differences property, then we can prove exponential tail bounds on the probability of the deviation. So this is something called McDiarmid's inequality. It says that if x1 through xn are independent, no other assumptions on x1 through xn. But f satisfies the bounded differences condition, then the probability that f of x1 through xn deviates from its expected value by an amount greater than or equal to delta is upper bounded by 2 times e raised to minus delta square 2 delta square divided by summation I equal to 1 to n ci square, where these ci squares come from the bounded difference condition. So just this requirement that the function value doesn't depend too much on a single variable, that itself is enough to give us a sub-Gaussian tail bound on any arbitrary function. Note that there's a difference when we are going from say sub-Gaussian, sub-exponential random variables or sums of those random variables. In that case, we were essentially making assumptions on the random variables themselves, that they're either sub-Gaussian or sub-exponential. Right now, it's a shift in thinking in some sense, in that we're not imposing any constraints on the random variables themselves. They have to be independent, but that's it. But we're imposing constraints on the function. Can be any function, any weird function that you can't really compute easily, but as long as it doesn't depend too much on one variable, we can in fact derive exponential tail bounds. And many of these constraints can be relaxed. You don't even need something as strong as a bounded differences condition.
Here is the maximum differential change caused by it.
Exactly. The CIs are essentially the maximum deviation of the function for if you vary only xi. Right? This is a sub-Gaussian tail bound, yes. So in fact, if effectively what this is saying is that if f satisfies the bounded differences condition, then f of x1 through xn is sub-Gaussian, or the centered version of f of x1 through xn is sub-Gaussian. This holds for all delta greater than 0. Okay. So in fact, even if we have a slightly relaxed condition, which is if we have the following condition, which is a little more relaxed, if the summation I equal to 1 to n of z, or let me put it in this way, f of x1 through xn minus infimum of overall possible xi prime So if you let all other variables to be random, but look at the maximum deviation in only the ith variable, and these sum of all of these random variables is if this is less than or equal to some quantity v with probability 1, so these are all random variables, so we need some kind of a probabilistic bound on these. So if all of these are bounded by some, if the sum is bounded by some quantity v with probability 1, then again you can prove a similar exponential tail bound. Right? Sorry, I think this should be p squared. Okay, so this is a pretty nice thing. I mean, there are further relaxations of some of these conditions, and so as long as we have some kind of bounded variation in each of the coordinates, we can prove that the function is in fact sub-Gaussian. Okay. So another sort of class of functions of a similar nature are these classes of self-bounding functions. So what is a self-bounding function? So again, if we have any function, a non-negative function, we said that it has the self-bounding property if for each I mean it's you can think of it as some sort of a generalization of the bounded differences property. So for each I, if we are able to find some function where the ith function depends only on n minus 1 variables. The original function f is a function on n variables, and each of these fi's is on n minus 1 variables. So think of them as involving all of the, so fi involves all of the variables except the ith one. Right? So you just leave out the ith variable, but this function fi could be very, very different from f. That's one thing. So if for each I can find an fi which satisfies the following two properties, that is, for every x1 through xn, f of x1 through xn minus fi of the remaining x1 through xi minus 1, xi plus 1 through xn, if this is upper bounded by 1 and lower bounded by 0, and if I sum all of these, then this is upper bounded by f of x1 through xn, then this function is said to be a self-bounding function. And the nice property is that using the Efronstein inequality, you can show that if f has the self-bounding property, then the variance of f of x1 through xn is upper bounded by expectation of f of x1 through xn. Which one? Yeah, so you need some way to compute the expectation. That's a different story. But even if you're not able to find the expectation directly, this just using the Chebyshev inequality, it gives you some sort of a tail bound. Okay, and okay, so suppose I told you that the variance is less than or equal to expectation. What does this buy us? What can you say about the probability that f of x1 through xn minus expectation f of x1 through xn is greater than or equal to, let's say, delta times expectation f of x1 through xn? Right. So in other words, what is the probability that f is within 1 plus or minus delta of the expected value? I don't know how to use Chernoff for this, right? Because I don't know the moment generating function of f. The only thing I know at this point is this particular quantity. Great. So this is from Chebyshev's inequality. This is upper bounded by variance of f of x1 through xn divided by delta square expectation f of x1 through xn, the whole square. But I also have a bound on the variance itself. I know that the variance is upper bounded by the mean. So this is less than or equal to one of the expectations in the denominator cancels out. So this is less than or equal to 1 over delta square times expectation f of x1 through xn. So in many problems of interest, we have situations where the expectation itself is fairly large. Maybe it grows with n, but maybe it doesn't grow, say, linearly with n. Maybe it grows as log n or something. Right? Then at least this Chebyshev inequality, for if f has the self-bounding property, then the probability of this particular deviation is upper bounded by 1 over delta square, say, log n. Right? So for any delta greater than 0, I get a reasonably good bound. Right? And in fact, we can prove something stronger, although we will not prove it in this course. It requires a lot more like technical work, but you can show that if f has the self-bounding property, then f of x1 through xn is in fact sub-Gaussian. So that's a really powerful statement. Then again, you can prove an exponential tail bound. These two minus delta square divided by essentially 2 times the variance, or 2 times expectation of f of x1 through xn the whole square. Any questions? Okay, so let's see some examples to see how these can be used. Okay, so really the trick is there are these bunch of concentration inequalities. You have to know that these exist. But in most problems, the real innovativeness lies in trying to bring it down to this particular form, trying to find out which concentration inequality you need to use and how, and really show, let's say, show that the function is self-bounding, or it has boundary differences, and find all of the CIs. Right. The main challenge typically lies there. Once you're able to do that, once you're able to, let's say, compute the expectation, the rest of the analysis becomes fairly easier. Okay, so let's see another example. In the last class, I showed this example of bin packing. Let's take another example of finding the longest common subsequence. Okay, so this is the following problem. You're given two sequences, two random IID sequences. Okay, need not be identically distributed, but independent sequences. So you have x1 up to xn and y1 up to yn, all independent entries. So you have 2n random variables. All of the variables are independent, need not be identically distributed. But we'll assume that all of them are over the same alphabet. Okay. So you can think of this as two different sequences, x and y. And what we want to know is what is the longest common subsequence between x and y. So what do I mean by a common subsequence? So given two sequences x, y, a common subsequence is essentially some, let's say, x. So we basically find some I1 less than or equal to I less than I2 less than I3 less than IK, J1 less than j2 less than j3 less than jk, such that xi1 equal to yi1, xi2 equal to yi2, xik equal to yik. So for example, if I had two sequences and maybe the right, so this is my x and this is my y, then one common subsequence could be, well, a and then g and c. This is one common subsequence, right? But it's not the only common subsequence. I can also find another common, like other common subsequences. So t, and then I can maybe look at this g, and then another g, and then a c. So the first one was a common subsequence of length 3. The second example is a common subsequence of length 4. Right? So the length of the longest common subsequence is really what we are interested in. Now for two given strings or even two random strings, we don't have an expression for the longest common the length of the longest common subsequence. It's a complicated object, but the longest common subsequence again has you can definitely bound the variance of the length of the longest common subsequence using the Efron-Stein inequality.
Why this needs to be done?
Again, the problem is not to compute the longest common subsequence. So what we want to know is what is the behavior of, so if I'm given two random strings, then can I say that the longest common subsequence is, say, close to something with high probability?
Is it we are designing randomized algorithm?
No, we are not designing randomized algorithm. So this randomness is given to you, okay? And the goal is to understand if this concentrates at all.
What are the support of the
Something, it's the same. That's it. You have two sequences, both of them have the same support. They're independent. They need not even be identically distributed. But of course, I mean, you need some more additional assumptions if you want to say something more. If you just want a bound on the variance, then this is sufficient. They just have to be independent. Okay. Now, let f be f of x, y. Be the length of the longest common subsequence. Okay. Computing the expectation of f of xy is very hard, because even if you assume that, say, x1 through xn are, say, uniformly distributed between 0 and 1, or even so even in this particular case, sorry, even if the, let's say, Bernoulli half, an exact expression for f of x comma y is not known, even asymptotically. All right, there are bounds known and these bounds don't match. So they're between like 0.6 and 0.8 times n, right, for large enough n. But the Efronstein inequality allows us to compute or at least upper bound the variance. So suppose I change so remember that this involves 2n random variables. Suppose I change the value of one of these values. Let's suppose I change xi while keeping everything else the same. By how much can the length of the longest common subsequence change? 1, right? The same holds for yi. If I change yi, the length of the longest common subsequence changes by at most 1. So then this is a bounded difference. This satisfies the bounded differences property with Ci equal to 1. Right? So what can I say about the variance? Yeah? Yn squared? Correct. What is Ci? 1, correct. How many variables do I have? Correct. So you have 2n variables. So this is summation I equal to 1 to n Ci square divided by 4. Ci square is 1, and so in some sense I should take j equal to 1 to n. So let me call this Cx of I square plus Cy I square. Right, so this is n by 2. So all I can say is that the standard deviation is at most square root of n. Right, so at most what square root of n by 2, but it grows as order square root. I'm sorry, sorry, the whole thing divided. Correct. I could just take 1 to 2. There are a total of 2n variables. So, I mean, in these two examples, the application was kind of straightforward, not very hard at all. But at times it requires some creative thinking. So let's take another example of the largest singular value of a random symmetric matrix, or the largest eigenvalue. Okay, so the assumption is that we have a random matrix X which is symmetric, all right, and all the xij's are independent. Okay, of course, xij is equal to xji. So for all j greater than or equal to I, the xij's are all independent. So these are independent, need not be identically distributed, but I'll make another assumption that each xij is bounded. Without loss of generality, I'll assume that it's bounded by 1. My goal is to understand what is the largest largest eigenvalue of this symmetric matrix. So let me call this lambda max of x. All right. Just, I mean, even before we sort of go ahead, I'm making no assumptions on the distribution, but at least let us get a sense of how large or small lambda max can be. Right? How large can it be? Any guesses? Summation? Okay. Which could be n, right? Can you give an example of a matrix for which lambda max is equal to n? What are the eigenvalues of the identity matrix? First entry, but that doesn't satisfy this. Let me take these raws together. What do you mean? What would be the largest eigenvalue of a stochastic matrix? You're close. Let's just take the all ones matrix. What would be the largest eigenvalue of the all ones matrix? N. Why?
Take subtract minus it.
Okay, I mean, why is the largest eigenvalue equal to n? You multiply it with the all ones vector. What do you get? All n's, right? So it's n times the all ones vector. So all ones vector is an eigenvector, n is an eigenvalue for sure, and it's a rank 1 matrix. So how many non-zero eigenvalues can it have? Only one. So it is the largest eigenvalue, right? So the largest eigenvalue of matrices that satisfy this can be as large as n. In fact, one can even show that they cannot be any larger than n. And fine, smallest, sure, but they can also be negative, remember, right? Can you construct a matrix with largest eigenvalue equal to minus n? What would be the largest eigenvalue in that case? That would be 0. So minus n is an eigenvalue of that matrix, but 0 is the largest eigenvalue, right? Anyway, so we know that it can vary a lot, right? It can grow with n. The largest eigenvalue can essentially grow with n. Okay? But we'll see a surprising upper bound on the variance of any such matrix. So let's look at the largest eigenvalue. What is a way? It's a symmetric matrix. So what can you say about the largest eigenvalue? Is there some kind of an expression for this as an optimization problem?
Maximum of how much?
Okay, an easier way is the largest eigenvalue is the supremum over all vectors v such that which have, let's say, unit norm of v transpose x v.
leaders because the two norm of
The two norm of
ideally
what?
it should be two norm, some norm of the
Okay. What do you mean some norm of the matrix?
when we take maximum the largest value is the largest value.
Okay, so this is what it is, right?
Are we assuming any cautious?
No, this is essentially a consequence of the spectral theorem. The symmetric matrix, yeah, it's just the spectral decomposition, nothing more. All right. So, I'm sorry. So that's for a specific example. All right. If I take X to be a deterministic matrix, the all ones matrix, so if I take, so what would lambda max of the all ones matrix be?
Why have we found that we know unum of V should be 1? Like, can take other eigenvectors. Are the eigenvectors assumed to be unitary?
Well, if I didn't have this, then I would have to divide this by the two. What is
Just that, right? Like,
just that, nothing else.
we are not bounding to those eigenvectors and
I'm sorry,
we are not restricting ourselves to the space of eigenvectors with norm 1.
it doesn't matter, both of them are equivalent.
No, dividing by norm we end. In
Correct.
that case, we'll be reducing the eigenvector.
I don't care about what the eigenvectors are, right? I'm only interested in the largest eigenvalue. What is the value of the largest eigenvalue? And the nice thing about this particular form, we'll see it a little bit later as we go on, but the nice thing is that this is just a quadratic in V. Right? Of course, I'm adding additional constraints, but this expression is easier to work with.
I just the confusion about like how will it still get the largest lambda? I suppose some V existed that 2 norm of V is not 1.
So if you take any eigenvector, you can always normalize, right?
You can normalize. That's what I was asking. Are we normalizing and putting it or just restricting it? It's not restriction, right? It is normalizing it.
It's just a normalization. Yes. So this does not impose any sort of a restriction.
It's still going through the entire eigen.
You are going through the entire space, except that I'm just normalizing everything. That is all. Nothing else. Okay. So going back, so suppose I take the all ones vector. What would the largest eigenvalue? Sorry, all ones matrix. What is the largest eigenvalue? So you agree that n is an eigenvalue, right? What would be the remaining eigenvalues of this matrix? Zero, and why?
Like, the sum of the eigenvalues will be the like the trace of the matrix.
Okay, but that doesn't necessarily. All the trace says is that the sum of the eigenvalues is equal to n. Okay, something more. What is the rank of this matrix? 1. And how many non-zero eigenvalues can you have in terms of the rank? The number of non-zero eigenvalues can be at most the number of non-zero eigenvalues. So the number of non-zero eigenvalues is equal to the rank of the matrix, right? For a square matrix. So this matrix has one eigenvalue equal to n and n minus 1 eigenvalues equal to 0. So the largest eigenvalue is just equal to n. Is that okay? Okay. I mean, this is just to get a sense of how large, like if I just, even though I impose this condition that the absolute value of xij is at most 1, the eigenvalue, the largest eigenvalue can be as large as n. Right? That's the only thing I'm trying to point out here. Can be as small as, let's say, 0 or even go negative. It can go as large as n. Okay? So, and in particular, therefore, if I can choose distributions for which the expected value of the largest eigenvalue can be as large as linear in n, because this is one specific example. Okay, so with me, is this okay so far? Fine. So this is the largest eigenvalue of this particular matrix. I somehow want to use the Efronstein inequality in order to derive an upper bound on the largest on the variance of the largest eigenvalue. So in order to do this, let's say I do the following. So X is a random matrix. Let X ij prime be the random matrix that I get if I just replace the ijth entry of X with an independent and identically distributed value. Or maybe just to avoid confusion, let me call this X. So I'm keeping all of the other entries the same, only the ijth entry is replaced with an independent and identically distributed realization. Okay. So let's suppose that lambda is equal to lambda max of X, which is equal to say V transpose X V, where this V is the eigenvector corresponding to the largest eigenvalue of X. Okay, I'll write this in an equivalent form, also equal to the maximum overall U norm U equal to 1 of U transpose X. Because I mean here I'm specifically assuming that V is the eigenvalue is the eigenvector corresponding to lambda max. So X times V is nothing but lambda times V, and U transpose V is maximized only when U equal to V, if I'm maximizing overall unit norm vectors.
The same thing if you replace V by U.
That's there. I want to write this in this specific form. We'll see why. Okay. Now, so let me just look at this specific random quantity, lambda minus lambda ij. So similarly, I'll define lambda ij to be the maximum overall U such that norm U equal to 1 of U transpose X ij times V. Remember that V is the eigenvector corresponding to X. Anyway, so let me just look at lambda minus lambda ij plus, which is just, so this is equal to lambda minus lambda ij if lambda is greater than or equal to lambda ij, and it's equal to 0 otherwise. Just the positive part of lambda minus lambda ij. So this is equal to max overall U with norm equal to 1 of U transpose X ij, sorry, xv. Yes.
Lambda ij is multiplied xij with lambda.
Xij with no, right? Why? So remember, lambda ij is something that's a function of the xij, where x is replaced with the ijth entry of x is replaced with an independent copy.
Xij is a scalar.
Xij, this x, again, it's a bit confusing notation, but x superscript ij is a matrix. It's an n by n matrix.
Xij entry is B.
Correct. Where the ijth entry of the original matrix X is replaced with something else.
V is the largest eigenvalue corresponds to the part
V is the eigenvector plus
eigenvalue of the matrix.
of X. Yes. Okay.
While writing the first thing, we are assuming is like corresponding to the largest eigenvalue.
Correct. Of
We are
X.
also of X, and we are also keeping the constraint that norm is.
We are also keeping the constraint that norm V is 1. Yes. It's the normalized eigenvector. Okay. So let's look at this minus again max overall U such that norm U equal to 1 of U transpose X ij V. Right. So essentially the main observation, the first observation that we want to make, in fact I can just have U transpose XU and U transpose Xij. Because I'll eventually I will want to use this particular part of the Efronstein inequality which bounds the variance in terms of expectation of just the positive part of the difference.
But it is quite
Which one? That's okay. I haven't taken an expectation yet, so I'm still okay. All right. All right.
So the edge is already defined like this. Now we need the largest value.
I'm sorry, can you repeat?
So lambda ij
Correct.
is not necessarily the largest eigenvalue corresponding to the matrix.
So that's what I will want. So I'm sorry, maybe I should have changed this to
Is the
U.
degree of
I agree. Let's just have this. Now it is the largest figure. right? Correct. This is fine, right? But the one point that you have to note is that so if I so the first term over here is in fact equal to V transpose XV, right? This is equal to V transpose XV minus the maximum over all possible U with norm U equal to 1 of U transpose Xij U. Now, if I replace this, if I just look at V transpose Xij V, right, for a fixed V. Now, this V is really related to X, not Xij. This quantity can only be less than V transpose Xij V. Which one? So these two are U's. Okay, let me perhaps change this to maybe W if you're having confusion. All right. So, yeah.
Can you also tell why exactly we're writing the plus in the
We're using the ultimately I want to use this particular statement of the Efronstein inequality, which says that the variance of Z is upper bounded by summation I equal to 1 to n, expectation of Z minus Zi prime the whole square plus, right? And what is Z minus Zi prime plus? It's basically Zi prime is the random variable obtained by replacing xi with an independent and identically distributed copy, and plus is the positive part. So I want to get a bound on this quantity, which will give me a bound on the, which will eventually get me a bound on the variance. So by positive part, I mean the following. So given any number alpha, alpha plus is just max between alpha and 0. So if alpha is non-negative, then it's equal to alpha. If alpha is negative, then it's equal to 0. Okay, good. So, all right. So the second term, so I want to bound this particular quantity. The second term is equal to, is obtained by maximizing W transpose Xij W over all possible unit vectors W. So if I take a particular choice of W, then this value can only be less than the maximum. Correct? Which means that this gap can only be bigger if I choose a particular W. So let me choose W equal to V. Okay? Then this is less than or equal to this. Alright?
lambda is the largest eigenvalue?
Correct. So lambda ij is, it's essentially lambda max of X minus lambda max of the matrix Xi. Okay. Okay, this is fine so far. Because this is equal to maximum of this minus maximum of this. If I choose a particular V, say the following. So let's look at V transpose X ij v versus max overall w with norm equal to 1 of w transpose x ij w. What can you say about the relationship between these two?
Is it combined with
Why not? So v is a unit norm vector.
is it
Doesn't matter. V is some unit norm vector. You fix any arbitrary unit norm vector you want. Okay? Can I say that this is less than or equal to this? Because after all, I'm obtaining this by maximizing overall W. So for a given W, it can only be less than or equal to the maximum. Correct? So the negative is greater than or equal to the negative of the maximum.
because we use
Correct.
the largest eigenvector corresponding to
I'm assuming it's the normalized eigenvector corresponding to the largest eigenvector. Yes. That's what I'm assuming throughout. Okay. So let me make this. The assumption is that V is the unit norm corresponding to lambda max of x. Okay, fine. Now this is equal to V transpose x minus xij v. Correct. Now what does x minus xij look like? Most of the entries are going to be zeros. Which entries are going to be non-zero? Only the I comma j entry? Correct. It's a symmetric matrix. So the ijth entry and the j comma ith entry are going to be non-zero. Correct. So what is this equal to? What will it be equal to?
zeros.
So it's going to be something plus. It is going to be vi times xij vj. Sorry. Xij minus xij prime times vj plus vj times xij minus xij prime vi. Right? What do we know about xij minus xij prime? How large can that be? 2, right? So this is less than or equal to absolute value of vi, absolute value of vj times 2. Sorry, this can be 2. So at most. So essentially what this says is that if I replace the ijth entry of the random matrix X with an independent and identically distributed copy, then the largest eigenvalue of the largest eigenvalue can only deviate by this particular amount in the positive, whatever, negative direction. Okay. Now let me look at summation n of lambda minus lambda ij the whole square. It's a random variable. Remember, the vi's and the vj's, these are random variables that depend on x, right? They're not deterministic. So this is also a random quantity. What I need is an upper bound on the expectation of this particular quantity. If I can get an upper bound on this, then I can use Efronstein to get an upper bound on the variance of the largest eigenvalue. So this can be upper bounded. I mean, let me just directly apply to this for a given x. This is upper bounded by summation 1 less than or equal to I less than or equal to j less than or equal to n of 4 times, if I take this squared, then I get 16 times vi square vj square. Right? So this is equal to, this is less than or equal to summation I equal to 1 to n summation j equal to 1 to n vi square vj square times 16. Okay? I'm just adding it, I'm just over counting it. I don't care. Right? But what is this equal to? 16 times summation I equal to 1 to n vi square times summation j equal to 1 to n vj square. Yep, 2 norm square of vi and vj, which is what is a 2 norm of v? 1, right? So this is equal to 16, right? So this is it. Now I immediately get a bound on the variance. Directly from Efronstein inequality, the variance of lambda max of x is less than or equal to 16, an absolute constant. Which is really surprising because I made no assumptions on the distributions of the entries. And we know that lambda max can be as large as n, but it's
Applies only when the entries are between.
correct. The entries are between -1 and +1. Now, in general, I could have assumed that the entries are between, let's say, minus alpha and plus alpha. It has to be bounded, of course. But even in that case, I'd just get a factor of alpha square. That's it, nothing else. So it's the main point is that this is independent of n. So irrespective of how large your matrix is, the variance in lambda max is not much.
And we are always replacing only one entry.
Correct. Yes.
We can extend this to replacing two entries.
You could derive some kind of a bound, but that you probably only get something more complicated.
That case can be even interpreted.
Ultimately, you don't get much of an improvement. It'll probably just make it harder for you to analyze. Well, ultimately, the starting point is always this point in the Efronstein inequality. You typically start with this inequality And in fact, the rest of these are obtained by rewriting this or representing it in different ways. Self-bounding function, you won't get much improvements here, but there are many other problems where in fact you will get an improvement. Yeah, there are other problems. If you, for example, if you don't assume that the functions are bounded, sorry, the entries are bounded. Yeah, there are scenarios where, for example, you want to analyze the largest eigenvalue of a random symmetric matrix without this boundedness assumption. For instance, assume that the entries are Gaussian. Then can you derive an upper bound on, or can you derive concentration inequalities on this? In fact, right now we've only bounded with the variance for this largest eigenvalue, but in fact, what you can show is that the probability that lambda max of x minus expected value of lambda max of x is greater than or equal to delta is in fact decaying exponentially minus delta square divided by some constant. No. This is only for this particular scenario, right? Wherein the entries are bounded. You can prove similar tail bounds for the Gaussian as well, but you need something a little more. That's what I said. So even though we are using the Efronstein inequality to bound this, a lot of these results can be generalized. So in this case, we proved we had this slightly stronger condition in that I didn't really take the expectation, right? This was less than or equal to something with probability 1. In many cases, that's enough. So if you are able to show that this sum is upper bounded by some constant v with probability 1, then you can translate that into an exponential tail bound. If I'm only able to show that this is less than or equal to something in expectation, then usually it is not enough to get an exponential tail bound. But this is one of those special cases where you can get something strong.
We don't make any assumptions.
We are making some assumptions.
Apart from that,
No, we don't need any other. So yeah, in particular, I don't need to know what the distributions of each of the entries are. But in many cases, that boundedness assumption can be strong.
no, we are bounding -1.
Correct. Any other questions? Okay, so I think I have only about 15 more minutes. So perhaps very quickly, I'll give a sneak peek as to how we'll see if you're attending the Introduction to Statistical Learning Theory course, what will you see that is related to concentration inequalities. Right. So the fundamental problem that we'll see in Introduction to Statistical Learning Theory is the following problem. Let's think of the simplest problem in learning theory, which is, say, classification. So what is a classification problem? Let's think of classifying images as having a particular object, maybe having a car or doesn't have a car. The goal is to design such an algorithm to detect whether there's a car in an image or not. Okay. Now, we need to make some assumptions. We need some kind of a mathematical framework to analyze such problems. And the framework that we'll see is that we'll assume that there is some ground truth and the assumption will be that there is some unknown joint distribution x comma y on x, which is maybe the space of all images, and y, which is, let's say, +1 or -1. +1 if there is a car, -1 if there is no car. Okay. And we don't know what pxy is, but what we assume is that at any point in time we are presented a random sample that is drawn according to pxy. Okay. Now in this case, since we don't know pxy, we need something. So we'll turn to what is called the supervised learning framework. We are given a bunch of images, labeled images, and the goal is to design a predictor, design a classification algorithm that does a reasonable job. Okay, so we're given x1, y1 up to maybe xn, yn. This is all that you're given, and one assumption that we make is that these are all independent and identically distributed. So in some sense, this have to be representative of the ground truth. Okay, and they have to be informative in some sense. Because if they're all dependent, then you don't get enough information, and it has to be related to the ground truth. Otherwise, you can't really do anything much. All right. So given this, the goal is to design a predictor, and one particular popular approach, although it's not the only approach, is you consider a class of predictors. For example, it could be the class of all polynomials, the class of all linear functions, or the class of all neural networks with certain parameters. And you try to find the predictor that does the best within this class, find that set of parameters for which you do really well on this particular set of data that you have already seen. So this is an approach called empirical risk minimization. So let's think of an algorithm which does the following. It computes the minimum over some class of functions. This could be the class of all polynomials with degree less than or equal to 10, or it could be the class of all, say, one layer neural networks with, I don't know, 100 different parameters. Okay, and what you try to do is you minimize the so-called empirical risk, I equal to 1 to n. So for a given G, you find out for how many images did you misclassify. So you know the true labels over this set. Okay? And you find out for each G, let's suppose that you're able to compute what is a fraction of data samples over which you make a mistake. Okay? And you find that G which makes the least number of mistakes over your set of training samples or data samples. Okay? How you compute this, that's a different story. Right, but let's suppose that you're able to do this exactly. Okay. I'll call this particular function that I get, or particular predictor, Gn. Okay. Now there are a couple of things. The whole goal of statistical learning theory is to find out how well does Gn perform. Can we mathematically prove bounds on how well Gn will perform, particularly when n is large? These are the only assumptions that we can make. The only assumptions are that we know what the alphabet is, we know that xi, yi come from some joint distribution which is not given to us, but still we have to design a predictor. And this is going to be our rule for designing the predictor. Okay. So this particular quantity is what I'll call the risk or the empirical risk achieved by some predictor G. Okay, but really the fundamental quantity of interest is not how well you perform over this training set, but in fact if I present you a completely new sample drawn from pxy, then how well will it perform, right? Because that is a real quantity of interest. So what we want is to find out what is R of G or R of Gn, which is the expectation of, or the words, the probability that if I draw an independent sample, then the probability that this goes wrong. Okay. Remember, we don't have access to pxy. We don't know what pxy is. But still, we want to not just design a Gn, but also be able to somehow say whether R of Gn is going to be good. Remember, for Gn, I can compute Rn of Gn, which is the empirical risk, but this risk is something that I cannot compute. You don't know what the true distribution is. So the main reason why concentration inequalities are useful is that we'll be able to say that even though we don't know what R of Gn is, if n is sufficiently large, then Rn of Gn is a good proxy to R of Gn. So as n becomes large, Rn of Gn concentrates, and it in fact concentrates to R of Gn. Now there's a subtle point over here. Although it may look like just an average of independent random variables, it's Rn of Gn is really not just a simple sum of IID random variables. And why is that the case? It's because of this minimization. So for every data set or every sequence x1 through xn, the minimizer could be different. What you can very easily show is that for a given G, the probability that G of Rn of G minus R of G, this is greater than or equal to epsilon. This decays as e to the minus n times epsilon square divided by a constant. That's not very hard to do for a fixed G. Okay? But this Gn is not a fixed G. It depends on what samples you have seen, because it was obtained by. I'm sorry?
For a fixed data set.
For a fixed data set is fixed, but then that's what we want to know, right? It's over this random data set that we want to know whether it approximates R of G or not. So life is complicated because of this particular minimization. And we are not able to use, say, something like a Chernoff type bound anymore. So in fact, in the course, we'll first try to apply Chernoff type bounds. That's going to be a starting point. We see that we know that this gives an upper bound, and suppose that the class of functions G is finite, then maybe I can just take a union bound and get an upper bound on this. So that will ensure that will give me a bound on probability that Rn of Gn minus R of Gn is greater than or equal to epsilon. Somehow, so my goal is to somehow try to bound this. Okay. So just the combination of this with a union bound will give me something, but that bound will only be helpful if G is not too large. In fact, it has to be finite and it can't be too large. But even if G is not finite, we'd see that there are some techniques that we can apply in order to still apply some sort of a union bound and get something informative. But even that won't be enough. So we'll see how we can try to apply things like the McDiarmid's inequality and other such concentration inequalities, not for averages, but rather more complicated functions. That's where the utility of these self-bounding functions and so on lie. So even though your actual function is something very, very complicated, just by having these nice properties helps you derive tight concentration bounds. So much of the course will be in trying to analyze this so-called risk for slightly more generality, and try to see what we can say about, let's say, performance of algorithms such as empirical risk minimization, which is really the workhorse of most machine learning algorithms today. Much of, say, deep learning or modern machine learning algorithms are mainly, what they mainly try to do is solve this in an efficient manner. How do you solve this optimization problem? Whereas in statistical learning theory, you're not worried about how you perform this minimization. You're only interested in knowing, okay, suppose I am able to perform this optimization problem exactly, what does that buy me? Is it good enough? All right. Okay, so maybe I'll stop here. Are there any questions related to today's lecture or anything else? Yes, that's what it's going to be mainly be about. Correct. That's right. Thanks. It is the R. Any other questions or comments? Next Monday? During class hours. That was announced in the very first lecture. Any other questions?